Now we're going to look at some word problems, these variation problems, and we start with just a little bit of language. If we say that y varies directly as x, that means that y is equal to some constant times x, right? Y is kx for some constant k. Varies directly as means the same thing as y is proportional to x. If y varies inversely as x, that means that it's some constant k divided by x. So a direct variation means that as one quantity grows, so does the other. With inverse variation, as one quantity grows, it causes the other one to shrink. If y varies jointly as x and z, it means that it is some constant times the product, x times z. We call this number k the constant of proportionality, and a lot of what we do in this section is just going to be kind of parsing out a problem and trying to figure out then how we set up the equation. So a quick example, let's say we know that the circumference of a circle varies directly as the radius r. So this, just as a statement, c varies directly as r, we would say, oh, it's some constant k times r, which is true. Now we happen to know what that constant is. That constant is 2 pi, right? Because we know that a circle is equal to 2 pi r. We know that the area of a circle varies directly as the square of its radius. So the area is some constant k times the square of its radius, so that's r squared. And again, we happen to know what k is in this case. K is equal to pi, right? We're very familiar with the formula a equals pi r squared. In chemistry or physics, Boyle's law states that the pressure of an ideal gas varies inversely as the volume. So that means as the volume increases, the pressure decreases. And P varies inversely as the volume, so it's some constant k divided by volume. And then another formula from physics here, Newton's law of universal gravitation, says that the force of gravitation between two objects varies jointly as their masses m1 and m2 of the objects, and inversely as the square of the distance between their centers. So we can write this as an equation. A variation equation can involve more than one kind of variation. So the force is, it varies jointly as m1 and m2. So some constant k times m1, m2, and inversely as the square of r, so that means we're going to divide by r squared. And there is the law of universal gravitation. Solving a variation problem involves kind of the following steps. You know, they're going to describe it in English, and the first thing we do is try to write the general equation that models the statement, just like we did. Like what we did in these examples, we wrote a general equation, right? A is equal to k times r squared. P is equal to k over v, right? Like that's what is described when they say that this varies inversely as the volume v. Okay, so we write that general equation. Now, then we want to find k. And usually they're going to give us like maybe some matched pair values that allows us to find k. Then we call that, once we find k and put that in the equation, that's the specific equation for our problem. And then once we have that specific equation, we can find what they're asking us to find. So for example, in example 10.7, they tell us that y varies inversely as x. So I'm going to stop there. I'm not going to read any further. Y varies inversely as x. So that's enough for me to get the general equation. It's equal to some constant k divided by x. So that's step one. Now, they say that x is 15 when y is 4. So here's the sort of specific information they gave us that's going to allow us to find k. So I'm going to plug that in. Y equals 4, x is 15. So now we can solve for k. Multiply both sides by 15. And we get k is equal to 60. And then we're going to take this k equal to 60 and put it back in the equation. So now here's our specific equation. Y is equal to 60 divided by x. Okay, now we can answer the question. Find the value of y when x is 12. Okay, so (60) divided by 12 is 5. There we are. So this is basically the process, the procedure that we go through. Let's do another. Find r when n is 16. That's our goal. If r varies directly as the square root of n, so not as the square of n, but as the square root of n, and r is equal to 4 when n is 25. So this part here I just put in the box. I'm going to use that first. R varies directly as the square root of n. That means that I can get my general equation out of that. R is equal to some constant k times the square root of n. And then they give us this specific information. R is 4 when n is 25. There's our sort of matched pair of values. So 4 is equal to k times root 25. 4 is equal to 5k, and if we divide by 5, we get k is equal to 4/5. Now that means that our specific equation is r is equal to 4/5 times the square root of n. And now we could do what they asked. Let's find r. I need to cross it out. Let's find r when n is 16. So we get 16/5. And there's our result. Okay. So let's do another one. Let's do maybe a more interesting word problem. In a couple of pages ago, a few examples back, we wrote an equation that models or describes Newton's law of universal gravitation. So that was the one that said that the force of gravity between two objects varies directly as, or varies jointly as, the masses, m1, m2, and inversely as the square of the distance between them. So there's this general equation. Here's our problem. A spacecraft is traveling from the Earth to the Moon, which are 240,000 miles apart. And I'm going to take that distance as being from center to center. So overall, let's say here's the Earth, here's the Moon. That is 240,000 miles. And we have a spacecraft traveling from one spot, from the Earth to the Moon. We want to know how far from the Earth is the gravitational force on the spacecraft equal to the gravitational force of the Moon on the spacecraft. So as the spacecraft moves from one location to another, its distance is changing, and so it's going to feel a force of gravity from the Earth. It's going to feel a force of gravity from the Moon. And we want to know at what point along its journey is the force of gravity that it feels from the Earth equal to the force of gravity that it feels from the Moon. Okay, so let's say that happens here, and I'll call this distance r, and so that means this is 240,000 minus r. Also, we have some masses to deal with here, so I'll let m sub e be the mass of the Earth. M sub m can be the mass of the Moon. And m sub s will be the mass of the spacecraft. Okay. Now they tell us some stuff. They say that the mass of the Moon is 0.0123 times that of the Earth. So we know that m sub m is 0.0123 times m sub e. And we want to know where's the force that the spacecraft feels from the Earth equal to the force that it feels from the Moon. So overall, here's what we want our equation to do. We want force from the Earth to be equal to the force that it feels from the Moon. And so I'm going to use this expression here, set those forces equal to each other. So the force from the Earth will be some constant k times the mass of the Earth times the mass of the spaceship divided by r squared, right? Because r is the distance from the Earth to the spacecraft. And then the other side will be some constant k, same constant k, times the mass of the Moon times the mass of the spacecraft, divided by, now the distance from the spacecraft to the Moon is 240,000 minus r. So this would be 240,000 minus r, and then squaring that. Okay. Excuse me. Now we know that the mass of the Moon is 0.0123 times the mass of the Earth. So I'm going to put that in there. And further, we know that k, m sub e, and m sub s are all constants, right? Their masses aren't changing. We're going to neglect the mass of fuel for the sake of simplicity. The fuel does not add a whole lot of the mass, and I think that's a reasonable assumption to make. So k, me, and ms are all constants. And so that means that the product, K, M, E, M, S, is also a constant. Let's call it C. So that means that this is equal to C, and also that product is also equal to C. That simplifies things quite a bit here. So you have some constant c over r squared is equal to 0.0123 times c over 240,000 minus r squared. And now, even better, let's just divide both sides by c, or multiply both sides by 1 over c. We get some canceling here. So now we really, honest to goodness, have an equation with only one unknown. That's a pretty sweet spot to be. This is a proportion, and then I've got just one equation, or one fraction equal to another fraction. Let's go ahead and set the cross products equal to each other. So when we do that, we've got 0.0123 r squared is equal to 240,000 minus r all squared. Now there's more than one way we could do this, but But I think the easiest way will be to just proceed by taking the square root on both sides. R is a distance, and it's going to only be a positive. So when I take the square root, we should only need to consider the positive root. So I'm going to take the square root on both sides. On the left, I need to know what's the square root of 0.0123, so I'll just throw that in the calculator. I get 0.1109, so I get 0.1109R equals 240,000 minus R. Now we just need to add R to both sides, and that will give us the following equation. If I take 0.1109R and add 1 R, we get 1.1109 R. This is equal to 240,000. And now it's all over but the shouting. We'll just divide by 1.1109. You get 216,041 to the nearest mile. And that is how far it is from the Earth when the force of gravity it feels from the Earth is the same as the force of gravity it feels from the Moon.